You used to call me on my cell phone.
The aerospace sector is booming. Last year, worldwide space budgets hit a record of $106 billion and launch activity surged by 18% with 221 rockets and nearly 3,000 satellites launched. Yet, despite decades of progress, one fundamental challenge remains unresolved: atmospheric re-entry. At hypersonic speeds, air in front of a spacecraft is violently compressed, heated, and ionized, forming a dense plasma sheaf. This plasma creates three simultaneous problems: extreme thermal loads, severe aerodynamic drag, and complete communication blackout. Current solutions rely on heavy passive thermal protection systems, ablative shields or ceramic tiles that are costly, maintenance intensive, and fundamentally limited.
This raises a question: what if plasma were not merely a destructive byproduct of re-entry, but a controllable physical medium? That question is the foundation of our project, Photon-Shaper. In practice, a forward-pointing laser will pre-ionize the column of air in front of the craft, and onboard, magnetic coils will apply Lorentz forces to steer the resulting plasma. The idea is to form a controlled dome-shaped plasma barrier that envelops the vehicle's nose. This active plasma bubbles takes the heat, loading, and the shock of the hull, while also retaining the conductivity in the plasma for magnetic control. In effect, Photon-Shaper is a dynamic, tunable shield, a kind of plasma lens riding the bow shock. This concept is grounded in recent plasma aerodynamics research. Reviews of opposed plasma flow control know that ultra-fast discharges can actively reshape shock waves and high-speed flows. In one notable experiment, scientists fired a terawatt femtosecond laser in front of a Mach 3 model that created a thin hot air column that had the aerodynamic drag. Photon-Shaper builds on these things. It combines laser-induced ionization with magnetic confinement to form a reusable shock absorber. We draw from this report science, using directed laser pulses to trigger ionization, then leveraging established electromagnetic theory to sculpt the plasma. A pulse laser is aimed ahead of the vehicle. When the laser fires, it creates an optical breakdown in the air, instantaneously ionizing it into plasma column. In nanoseconds, we get a burst of electron and ions in the proper location. Surrounding the vehicle's nose are magnetic coils, generating a strong magnetic field. A charged plasma from the laser feels the Lorentz force and is driven to the particular geometry by tuning the current and the fuse shape. We can pull the plasma into a dome ahead of the nose rather than letting it disperse. Embedded sensors monitor the local plasma density and shock position. This data feeds a control loop. The onboard computer adjusts laser pulse timing and the coil's current in real time to maintain the optimal plasma configuration as flight conditions change. In our lab prototype, we use a 100 megajoules pulse laser diode with focusing optics to recreate centimeter scale plasmas. Helmholtz coil powered by a capacitor bank generate a few hundred Gauss fields. We have instrumented the setup with high-speed photodiodes with mini plasma probes. In test, at a low pressure, even this molded system produces a visible plasma ball deflected by a magnetic field into a partial dome. These principal echo current research, nanosecond laser discharges, and plasma actuator have demonstrated shock control and drag reduction. Photon-Shaper extend them into a unified shield.
Beyond physical prototyping, we recognize that a system as complex as plasma control re-entry must be understood at the systems level. That is why we developed the Photon-Shaper Virtual Lab. A Photon-Shaper Virtual Lab is a three-dimensional digital simulation environment built entirely in Python, designed to study laser-based plasma control during atmospheric re-entry. Rather than isolating individual effects, the Virtual Lab integrates orbital trajectory, atmospheric density variation, convective heat flux, plasma sheaf formation, and radio frequency communication blackout into a single coupled model. Using established preliminary physics model, such as exponential atmospheric density, a simplified Sutton grades heating formulation, and plasma density thresholds associated with RF blackout, we simulate how plasma naturally forms around a re-entry vehicle. Within this framework, the Photon-Shaper is modeled as an active control mechanism, selectively reducing plasma density through directed laser energy deposition.
Photon-Shaper offers distinctive advantage over existing solutions. Active and reusable, unlike labeling, heat shields, or single-use tiles, our system can be turned on or off as needed. There is no consumable material eroded on each flight. Once the laser and coils are installed, they serve indefinitely. This means reusability and mission flexibility. Real-time control, because we actively generate a steer plasma shield. The shield adapts instantly to changing speed and angles. Traditional TPS is fixed in form. Photon-Shaper can tune the plasma envelope on the flight. Plasma actuators are known for nanoseconds response times and operate across a wide flight envelope, so our shield can respond faster than mechanical systems. Lightweight and low power. The hardware has surprisingly low mass compared to heavy ceramic tiles. Plasma flow control research highlight that low-temperature plasma actuator provides strong effects with relatively little power. Photon-Shaper channels energy directly into the shock rather than heating tons of material up, offering an inherently efficient shield.
The potential markets span aerospace and defense. Space re-entry vehicles like NASA, ESA, and commercial space companies all invest heavily in TPS. Every crew capsule and cargo return vehicle needs reliable, reusable shielding. As more missions return spacecraft through atmosphere, demand for advanced TPS roads. Hypersonic aircraft and missiles. Militaries around the world are racing to deploy hypersonic cruise missiles and glide vehicles. These systems require TPS that survive Mach 5+ flight. Analysts project the hypersonic flight market at over $1.3 billion. By the early 2030s, a plasma shield could give these vehicles longer life and better performance. Furthermore, reusable spaceplanes and SATO. So these future single-stage to orbit and hypersonic passenger aircraft will be made extremely lightweight, reusable thermal protection. Photon-Shaper directly addresses their needs by replacing heavy tiles with an on-demand shield. In addition, the Tantallo forecast the thermal protection systems market to surpass $10 to $12 billion by 2033. These figures highlight that our target segments are large and expanding. Our commercialization strategy is partnership-driven. First, we'll focus on academic and industry collaboration. We'll co-develop Photon-Shaper with aerospace universities and national labs. For example, NASA's Aerothermodynamics centers to refine the technology. Joint research papers and flight experiments will also build the credibility. Next is our grant and licensing model. Initially, we'll seek research grants to fund the prototypes. In parallel, we'll find provisional patents. And in the long term, we'll plan to license the core IP to establish aerospace OEMs and defense contractors rather than build full systems ourselves. Then, we'll proceed to partner-led market entry. We'll target prime contractors like Airbus, SpaceX, and military labs with white papers and concept demos. We employ a credibility-first approach, focus on validated data and small-scale demonstrations before pitching large contracts. We also use permission-based outreach, engaging stakeholders one-on-one and building a following at conference.
In conclusion, imagine a future where every spacecraft hypersonic vehicle carries an intelligent, reconfigurable plasma shield. Photon-Shaper aims to elevate that safety to a new level by adding reusability and active control.
We are a passionate, student-led research team with a bold vision. Our lab research hint at the transformative potential.
With the support, big mentorship, funding, or partnership, we can scale up this technology from the lab to the actual flight test. Join us on our mission to revolutionize re-entry shielding.
Together, we'll take the Photon-Shaper shield from our slide presentation to liftoff.